All right, recording's back going. Yeah, you guys are on and ready to play Kahoot. Here we go. Linear motion. One possible unit of speed. Yeah, this could all work. Okay, so miles per hour. Here's our American unit. That works. Okay. Kilometers per hour. Maybe cross over to Canada. I think maybe. Right. In this class, we tend to use meters per second. Okay. Light years per century. Guys, what is a light year? That's what. Yeah, it's actually a distance, right? It's yeah, how far does light travel in like one Earth year? Right? How far? Right? Which is a distance. A century is a time. You guys see that every single one of these is some kind of distance compared to time? Right? Distance over time? Yeah. There you go. So distance compared to time. Right. So lots of ways you can quantify that. Right. All right. Ooh, points on the board. First points of the year. Yeah. Object moves 5 meters in the first second of travel, 5 meters in the next second of travel, 5 meters in the third second of travel. What's the acceleration?
Wait, no, I missed it though. Already? No, yeah, you.
Yeah, zero. 0 meters per second squared.
Okay.
Guys, what about a slightly different question? Guys, what's the velocity equal to?
5 meters per second.
Yeah, there you go. The velocity is 5 meters per second. But that's constant, right? And acceleration is a rate change of velocity, but there's no change of velocity. It's just 5 meters per second. It's just going. It's just going, right? So no acceleration. You guys go with no acceleration, right? Because there's no change in its motion. It's just going. Right? All right, so we got Anna, Cole, Spencer, Olivia, Bruce. An object falls freely in a vacuum. What increases?
Oh, wait. No.
One winner.
Yeah!
One winner. One winner.
Acceleration
Yeah.
is a constant.
Yeah, acceleration's constant, right? Isn't that true? Like drop a ball off a cliff, wasn't it 10 meters per second squared all the way down? 10, 10, 10, 10. Right. So acceleration's constant. Yeah, velocity is increasing at a constant rate, but velocity is increasing. Yeah. Right. Yeah, so velocity increases. Right. No, that's true in a vacuum. Because what about okay, let's make this a little trickier. What if it what if it was not a vacuum? What if you bring in air drag? Okay. Guys, if you bring in air drag, do you think the faster it falls, it will be speeding up for a while, right? Okay. Do you think that air drag also builds up more and more and more? Right? Yeah. And that process continues until what happens?
They balance.
Yeah, until the forces balance and you have terminal velocity. Yeah, and at that point you have a really fast velocity, but you have no acceleration. Right? But you need air drag to make that happen. But in a vacuum, yeah, it'll just keep speeding up. Yeah. Okay. If you guys have any questions on these, let me know. All right, we got Cole, Spencer, Olivia, Bruce, Gavin. Ball's thrown straight upward and caught when it comes back down. In the absence of air resistance, its speed when caught is. Yeah, the same. The same as when it was thrown upward. Right. Here, I'll draw this out for you guys. Let's go. Let's go over here. How's that?
Yeah, because
Say you
it's around like grab. So it's
take a ball, throw it straight upward.
points no matter what.
Okay. Let's say initial velocity is 30 meters per second. 30 meters per second. Okay. So after 1 second, it's here,
And then put it.
and then 2 seconds, 3 seconds, 4, 5, 6. Okay. Maybe this horizontal axis is kind of like a time axis. Is that okay? Could this be like a time axis? I know it's kind of abstract. This could be 0 seconds, 1, 2, 3, 4, 5, 6. Is that okay? Okay. So 1 second, 2 second, 3, 4, 5, 6. Oh, I need to label my unit. Oops. Times in seconds. There you go. Okay. Okay. And then well, it looks like the way I drew this sort of have height, I guess, as a vertical axis. Maybe this could be height in meters. Okay. Yeah, let's go ahead and finish this out because I think this is gonna be helpful. Oh, actually, I should have my axis right here, shouldn't I? Oops. Anyway, you guys get it, yeah. Right. All right, let's call this height 0 right here. So 0 meters height. Okay. Um, actually, I think we did this the other day. Guys, what's the maximum height of this ball all the way up here? 45 meters. You guys remember that? 45 meters? We worked that out. Was it yesterday, I think? Okay, you throw the ball. Here, let's do this. Okay. You guys remember doing this? So if you throw the ball 30 meters per second, guess what's 30 squared? 900? Okay. And at the peak, wouldn't this be 0 over here? This would be 0. Right, and you sort of subtract this over. Right. 2 times 10 would be 20. Guess what's 900 divided by 20? So yeah, 45 right there. 45. This is 45 meters right there. Okay, so looks like the height source changing. But what about velocity? Okay, let's go back to velocity. Guys, how fast is this ball going up right here? You threw it at 30 meters per second. After 1 second, is it slowing down? It lost how many meters per second? Gravity's pulling it down. Guys, in Earth's gravity, velocity changes how many meters per second every second? Yeah, 9.8 or 10. Right? So, and the fact that you threw it upward, it's slowing down. So it slows down to how much? 20 meters per second. After 1 more second, it's going up how fast? 10 meters per second. 1 more second is how fast? 0 meters per second. We're talking about velocity. 0 meters per second. After another second, now it's going down. How fast? 10 meters per second. And then, yeah, 20 meters per second. And then this one's going down at, yeah, 30 meters per second. Okay. All right, is that okay? Okay. Now, what prompted me to draw this out is, do you guys see that at equal heights it has equal speeds? No, opposite direction, so opposite velocities, but equal heights is equal speeds. You guys see that? Okay. Now, hold on this idea because I think this ends up being really useful for some of the questions coming up. All right, so what we did here. We got Olivia, Talia, Spencer, Bruce, Gavin. Ball thrown upward, rises and falls back to the floor. During this time, acceleration is always. Wait, is gravity field kind of an acceleration? Which way does gravity always pull? Down. Gravity's down. Yes. Okay. Okay. Now, okay. A lot of you guys chose this gold one. Now, guys, what vector is always in the direction of motion? Not the acceleration, the velocity. Yeah, velocity always tells you which direction of motion. Right? Acceleration tells you which way it's tending or which way the net force is. Okay. Yeah, so it's always accelerating down. Okay. Right. Throw the ball up. Whether it's moving up or moving down, it's always accelerating down. Yeah. Got Talia, Cole, Bruce, Spencer, Gavin on fire. Suppose you travel 300 kilometers. You do that in 5 hours. What's your average speed? 300 kilometers, 5 hours. There you go. Yeah, 60 kilometers per hour. Right, it divvies out. Okay. Of course, that would be an average. Right. Yeah. Olivia, Cole, Bruce, Gavin, Spitzer, on fire. On fire now. Ball's thrown straight upward. At the top of its path, its instantaneous speed is. It's speed. 0 meters per second. Guys know that? So, and that would also indicate the point of maximum height. Zero velocity. 0 meters per second. All right. Ball's thrown straight upward. At the top of its path, it's acceleration. Ooh.
Wait, no. Oh, wait. Wait, the face already
Yeah, look at you guys. Look at you guys. Yeah, right. Guys, from the moment that you release the ball until the moment it crashes back to the ground, right? It's in free fall. It's always accelerating down at about 10 meters per second squared. Honor. Olivia, Bruce, Gavin, Cole, Spencer. Car accelerates 3 meters per second per second. How much time to get up to 15 meters per second?
Oh wait, squared.
Is that V equals GT? Or sorry, V equals AT, I should say. V equals AT. Okay, yeah. You guys good. Yeah. So, guys, it's that second kinematic equation. So it starts from rest, v naught 0. So it's just acceleration times time. So 3 times 5 is 15. That's all.
I was over.
You guys get 3 times 5 is 15? Yeah. 3 times 5. All right. Bruce, Gian, Olivia, Cole, Spencer. Freely falling object starts from rest. After falling for 5 seconds, its speed will be about. Okay. How do you guys get? Yeah, 50 meters per second. Here. So you guys know we're doing. I guess you could use this also, right? Start from rest. This goes to 0. 10 times 5 could be 50. Okay. Guys, wasn't that also this column right here? This one right here? This cell right here. Here. 5 seconds. It's picked up to 50 meters per second. Okay. Ah. Ooh. When you look at the speedometer of a moving car, you see that car's instantaneous speed. Yes, the speedometer tells you how fast the car's going at that instant, right? Average speed is like if you're going a long road trip, you say, well, I went many miles over many hours, and I kind of divide it up. Yeah, because the speedometer tells you at that instant. Same thing as the equations, because all the velocities that go in those 3 kinematic equations, those are all instantaneous values. Instantaneous. Got Samuel, Bruce, Olivia, Cole, Spencer.
Got it right.
Car starts from rest. After 5 seconds, it's picked up to 30 meters per second. What's the acceleration?
No, wait, what?
Ah! 6 meters per second squared.
Oh, it's the
So 5 times 6 is 30, basically. Right? So 6 meters per second squared acceleration times 5 seconds brings you up to 30 meters per second. Right? 5 times 6 is 30. Second kinematic equation. All right. 9 in a row. In a vacuum, objects fall at constant. Acceleration. Constant acceleration. Okay. Is that, sure you guys got this. Okay. Is that this column right here? Constant acceleration. Yeah. Hey, you guys got that? All right. Gian, Samuel, Bruce, Cole, Spencer. Keeping the lead. Oh, as drops of water fall from a leaky faucet. Do they get close together, get further apart, remain relatively fixed distance? Stay. Okay. Yeah, I'm looking for get further apart. All right, so a couple of you guys got that. Show you guys a picture. You guys see this ball falling off the edge of the cliff? What if this was like a leaky faucet going? You see these drops of water like spreading out. You see that? Because every second that passes, they're traveling faster. So yes, they spread out further apart. Okay, that's what the question was trying to get at. Yeah. So yeah, spread out. Get further apart. We got Samuel, Bruce, Gian, Cole, Spencer. Over 9,000. Bob can jump off the ground with twice the jumping speed of Alan. Just after his feet have left the floor. Is Bob's downward acceleration half of Alan's? Is Bob's downward acceleration twice Alan's? Or do Bob and Alan have the same downward acceleration? Right. After his feet have left the floor. flying through the air. Yeah, same. Actually, isn't that just the gravity field?
Yes.
All right. Again, after your feet have left the floor, the only force on you is your own weight. So you're accelerating down at about 10 meters per second squared. Or 9.8 if you like, meters per second squared. Guys good? Right. Guys, does that matter how fast you're traveling? Does it matter the mass of the players? Does it matter if they jump off at a 45-degree angle? Nope, none of that matters. As long as they're in free fall. If they're not standing on the ground, they're always accelerating down at 10 meters per second squared. All right, got Olivia, Bruce, Gian, Cole, Spencer. What is the value of G at Earth's surface? Yeah, about 10 meters per second squared, right? Yeah, so yeah, 9.8 meters per second squared. Okay. Guys, trivia question. Does anybody know what that is in feet? Feet per second squared? Anybody know? All right, so it's about 32 feet per second squared, but we're never really going to use that. But yeah, so 10 meters per second squared. All metric. Oh yeah. Oh yeah. The ball is dropped from the top of a cliff. Each second, its speed increases by. Yeah, 10 meters per second. That's what 10 meters per second is, right? Every second is increasing by 10 meters per second. Right, isn't that true? Right. I got Olivia, Bruce, Gian, Cole, Spencer. Ooh, who is a tight race? Look at those points. Yeah.
I think I have to.
All right. You drop a feather and a coin in a vacuum chamber. Which reaches the ground first? Yeah. Did I show you guys the video for that? No. Oh, here. I think I got time. Right, so
I do. I just.
so there's this big old vacuum chamber. Oh, here we go. I think it's slow motion. I don't think it's real time. But okay, yeah, there you go. It's one more time. So they're in a giant vacuum chamber. They suck out all the air. There's no air in there. They say it falling together. Bam. Guess that? Yeah. Oh yeah. All right. Okay. Ooh, I got another one. Okay, this guy's on the moon. He has a falcon feather and a hammer, and I guess, well, they could get to the moon, but they only had 19 of these cameras back then. So, all right. So he's got a feather and a hammer, and he's doing a very long explanation about physics. But he's going to drop them both at the same time.
The feather happens to be appropriately a falcon feather for our falcon, and I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
How about that? Oh yeah, how about that? There's no air on the moon, right? No air on the moon. Projectiles fired straight upward at 30 meters per second. How much time does it take to get back to the ground?
Oh wait, I'm just trying to. Kind of divided by very sure. Sorry, 30 divided by 10. Oh,
Yes, it's suspense. How many you noticed? That's this one right here. This one right here. Threw it up to 30 meters per second. After 1 second, it's here. 2 seconds, 3 seconds. Guys, it takes 3 seconds to reach the peak. And then does it take 3 more seconds to fall back down? What's the total hang time?
the referee.
6 seconds. 6 seconds, right? 3 seconds up, 3 seconds down. 3 up, 3 down. there's a few different ways to solve that. Here, real fast. There's okay. Guys, you could do that. You could split the problem in half, and you could say for this to go to 0, this would take 3 seconds, and then just double it by symmetry. You could say it starts out at 30 and ends at negative 30. You can plug in negative 30 here and positive 30 here, and we'll get 6 seconds, right? You could also, guys, how about this? If it starts and ends at ground level, what's the change in displacement?
What?
0. You could. This is a little tricky. You could plug in 0 right here, and you would plug in 30 here. You also get 6 seconds. So there's 3 different ways to do that. Yeah. So different ways to do that. I'll tell you 6 seconds. All right, we got Dion, Olivia, Bruce, Cole, Spencer. Are you guys ready for the win? For the win? Got 3 guys over 12,000.
I believe in you, Bruce.
For the win! Suppose a jumper claims at hang time. Some little kid comes up. I can jump. I'm off the ground for 6 seconds. If that's true, that jumper must be able to jump to a vertical height of what? I don't think it's realistic, but if it was somehow,
6 squared.
I know. If you jump off the ground and you don't land until 6 seconds later, I might have just flashed the answer.
Acceleration 6 squared. I really hope wrong.
If he jumps us in here, they can go up and then down.
Oh wait, no what?
Yeah, it's the egg. They don't look up in the air.
All right. So yeah. All right, guys. If you jumped in the air and you didn't land on the ground until 6 seconds later, isn't that also exactly this model right here?
Yeah.
Okay. Now I'm gonna cut that problem in half because at the halfway point that would be your maximum height. So it really takes how many seconds to reach the top? 3 seconds, right? And if you're either 5 and 3, or how about the other half of this? Guys, if you drop the ball and it takes 3 seconds to come back down, that's the second half of this. How far will it have fallen in 3 seconds? 45 meters, right? You guys remember ball off the cliff? 45 meters. Here, let me find that ball off the cliff. It's this right here. You guys remember 3 seconds fell 45 meters?
Then just compare it to
You can also use these. Yeah, this gotta be 45 meters.
That's not fine though.
So let's wrap this up. Let's see who won Kahoot. 45 meters. Are you guys good with 45 meters? Great.
The big chance.
If I had 10 more minutes of class, I would still walk some of these and solve them. But you guys see in principle how you could solve these. All right, to the podium. The podium. With the bronze, Spencer. With the silver, Bruce. And the gold is Cole. You have won Kahoot. And that's the class. That's a wrap.